normally the same as the number of classes.
Yes,
But
if you will use one hot encoding, right?
right, but you could conceivably find some form of encoding that would allow you to use at least one less. You could probably find some other strange encoding that would allow you to use maybe a square root amount of output nodes instead. Why would you not do that instead? Because then you would have fewer weights to train and thus presumably a better model.
So what will be the value of the output in this case? So if we have three classes, for example, so we can call it 0, 1, and 2, for example, right?
Sure, but take a larger problem instead. Let's say that you have 10 classes. Let's say that you're trying to do the MNIST dataset, hand-drawn digits dataset. If you have 10 classes, you can represent that as well, then you would need a 5-digit binary number, for
Yes, yes,
instance.
yeah,
And
I
and
agree
that
with
would mean that
you.
you would, instead of
Yes,
having 10 output
yes,
nodes, you would
correct,
have 5
correct.
output nodes, which would cut the number of weights to
Yes,
train in half.
I totally agree with you. Yeah, yeah, this is very correct. This is very correct. Yes. So it's just how you will code your classes. This is very fine. So for example, if we have five, you can just put it in binary format. How do you call it? Binary code or right? How do you call it?
You could
So
just encode it binary, so
you just
0 is
yes, correct.
0.
So it will be so. For example, if we have eight classes, for example, we can put them in 3 digits. So in this case, we can have 3 outputs. Yeah, I totally agree with you. No problem. Yes. It's just how you will do it. So it's up to you. But I'm just in general, people prefer to use, for example, one hot encoding because the output will be probability, for example. So the output will be probability that this image belongs to this class, for example. So if you will use one hot encoding, so in this case, number of outputs will be number of classes. But if you, it's up to you to decide how you will encode it. Number of
So
inputs.
one hot encoding is used because it's easier to distinguish the different outputs rather than because it's easier to
Yeah,
train.
yeah, it's just no, no, but it's not easy. I mean, the output anyway will be a number between 0 and 1, but when it's a probability, it will be much easier. But it's up to you. I agree with you that if you will do it like this, you will reduce number of outputs, and the model will be much less complex, in fact, which is brilliant. So I agree with you that this is very correct. So if you have 8 classes, you can just put them in 3 digits. If you have more, for example, like MNIST dataset, you can just put them in 4 digits, for example. So when it's a 0, 0, 4 zeros, it means it's a 0. When it's a 0, 0, 1, it's 1. When it's a 0, 0, 1, 0, it means it's 2. 0, 0, 1, 1, it's a 3, and so on. So I fully agree with you. So we need to simplify the model because when we simplify it, we will avoid, in fact, lots of problems. Because I have some examples maybe for next week where we have, especially when we are working with text, in fact, this sentiment analysis, we have the problem of overfitting. Overfitting, it's a very dangerous problem, and sometimes it's crazy. I mean, after the second epoch or the third epoch, my model went into overfitting, and it's hard to solve this problem, in fact. So the most important way for solving it, try to simplify your model as much as possible. And encoding, I mean, those classes into 3 digits or 4 digits, it will be also one good way for simplifying your model. So anyway, number of outputs will be number of digits, for example, or number of classes as you want. Number of inputs will be the number of features. The one in the middle here, it's hidden layer. If you want to go for one hidden layer or 2 hidden layers, it's up to you, in fact, right? Number of units in each hidden layer, it's up to you also. But I suggest that you start with a simple model, and after that, you try to increase the complexity step by step. Number of inputs will be number of features. So in the case of MNIST dataset, we have, I guess it's 784, correct? Pixel values. So the number of inputs will be 784. If you want to use BCA, I can just use BCA, for example, and I can use the first maybe 50 principal components. So in this case, it's one way for simplifying your model. If you will use principal component analysis, or if you will use an autoencoder. Because in fact, I have an example today. In fact, if we can finish it, I have an example today for training an autoencoder for dimensionality reduction. I can train an autoencoder to reduce the original number of features into a subset of features. So we can use autoencoder for this. So in fact, we can use BCA or we can use autoencoder. I mean, last year, for example, I had this question in the oral exam. I just asked the students, can you implement PCA using a neural network, for example? Can you use a neural network for dimensionality reduction? Yes, we can, because the autoencoder, in fact, it consists of two parts, encoder and decoder. And in the middle, we have a bottleneck. And this bottleneck, it will be the size of the code, which, so for example, the input will be the image, and I want to encode it, in fact, into a subset of features. So I can do this using an autoencoder. So today I want to talk about gradient descent. We talked about this before, in fact, and I need to apply gradient descent for 1D and 2D function. And after that, we need to talk about error backpropagation and implementing error backpropagation for a simple feed-forward neural network. And after that, applying it to Iris dataset. We did that several times before, in fact. So in the last 2-3 weeks, we did that a lot, but using MLP. We used MLP, for example, from sklearn, for example. And also we used from Keras, in fact, we used this model which called sequential, right? So we used this one. I mean, we used this one from Keras. We used MLP from sklearn, and we can build our model. So we can work as a black box, but we need to understand how error backpropagation works. So I mean, this introduction, it's just, we implemented those machine learning on computers, so the mathematical formulations are expressed as numerical optimization problem. I have feed-forward neural network, and it's impossible to find an expression for the error function. So we can differentiate it and we can minimize it analytically, in fact. As you can remember, in error backpropagation or in feed-forward neural network, we have a cost function which we try to minimize, which is error equal half multiplied by t minus y square. Do you remember this equation? So this equation, all the time we try to minimize it. We try to find the set of omega values, the set of weight, which will minimize this error function. So this is a loss function which we minimize each time. So here in this example, we have some weights here. So this one is omega 1,1, omega 1,2, and so on. This is V11, V12, and so on. We have bias values. So we have set of weights and we have bias values, and you need to find a good set for good values for those omega values and V values in a way to minimize this cost function, which is this one. So we use error backpropagation to do this, and this is the training process, in fact. This is what we call it training. So training and machine learning model often boils down to finding a good set of parameters. The notion good is determined by the objective function. How good and how bad? We need to find this using the value of E. So at the end, you have prediction error. So this prediction error, we need to minimize it as much as possible. How can we do this? By training. And in the training process, we will find a set of values. So we find the delta omega, and we adjust omega equal old omega plus delta omega, correct? And delta omega, it's minus eta, partial E by partial omega. So this is the equation, in fact, which we use in error backpropagation or gradient descent. We do this until we have a good performance or satisfactory performance.
Just checking, eta is the learning rate, right?
Yes, correct. Eta is the learning rate. And eta, it's a hyperparameter, which we need to select. You can just select a constant value, or you can select eta as a function of the gradient, which is more preferred, in fact. So I will explain it soon. Convex object function ensures the statement of reaching the global optimum. I mean, this one must be squared, right? In fact, we don't need to square it, but we just square it to be convex, right? When it's convex, it will look like this one, which means we need to reach this value. We have a guarantee that we will reach this global minimum at some point after some iterations. So, but of course, in real life, it's not convex. It's not like this one. It's bumpy a little bit. So sometimes it's like this one. So sometimes it has a global minimum and a local minimum. And the problem that maybe we can stuck in the local minimum. And in this case, it's a problem because I cannot train my model anymore because I cannot get out from this part here. We will stuck here. And if we stuck here, it's a problem because there is no way to get out from this one. You can get out from this one if you will select different random set for initializing your weights, right? And I will explain it later. So imagine we have a function like this one. Just we will start with simple example. This is an example. So if x equal x to the power of 4 plus 7 to the power times x to the power of 3 and so on. So this is a function, and we need to find x star, which will minimize this function. In fact, we need to find the value of x, which will make this function minimum. How can we solve this problem analytically? In fact, we need to get the first derivative, which is a gradient, df by dx. This is a gradient, and we need to equate. We need to set this equal to 0, right? So it will be 4 times x cubed plus 3 times 7, it's 21 x squared plus 2 times 5, it's 10x minus 17. We will set this one equal to 0. We will find values of x. We will factorize and find values of x. So we can get 3 values, right? So in fact, if you at each of those x values, this function will be minimum. In fact, this function will be 0. When you set x equal 0.7, this one will be 0. When you set x equal minus 1.4, this function will be 0, right? So it's minimum. But the problem now, how can we have 3 points, and we don't know which one is global minimum, which one is local minimum. So our function, in fact, it's the blue one here. So you can see that at that point, it's a global minimum here. At this value, the function it's a global minimum, right? At that function, it's maximum, right? Or global maximum, for example. This one here, it's local minimum. So this is the problem, in fact, in gradient descent. So in gradient descent, maybe we can stuck here, which is not the optimum solution. We need to reach the global minimum. So this is the problem. There is no guarantee that you will reach this one, right? So now I have 3 points. How can we differentiate between those 3 points? We can just get the second derivative and substitute each x value here, and we will see the value of d squared by dx squared, right? So here it will be positive. When it's positive, it means this is minimum. I mean the function is minimum. So in fact, d squared f by dx squared for this point, it's positive, right? For this point, it's positive, minus 1.4. No, minus 1.4, it's negative, and for this one, it's positive, right? So when it's positive, it means the function is minimum. When it's negative, the second derivative is negative. It means the function will be maximum at that point. So now we can select those 2 points. So those 2 points, in fact, one of those points will be global minimum, and one will be local minimum. How can we differentiate? We can differentiate between those 2 points by the value of the second derivative. The one which is more positive, it means this one will be the global minimum. So this is how we solve it analytically. But do you see, this function, it's not simple, but also it's much simpler than any feed-forward neural network.
Question.
Function, yeah.
So this the function f here is the transfer function of the theoretical system, right?
Yes.
Yes. So
no, this is the error function. This is the loss function, error function. You want to compare it with
f is the error function.
Neural network?
Well, yes, I would like this to sort of like what is it you're trying to say here, actually?
Yes. Now this one, if you want to compare this function, you can compare it with this error function, which is half multiplied by the summation of t minus y squared. So this is a function, in fact, in feed-forward neural network, which we want to minimize. We want to minimize e. We want to find the value of omega, which will make e minimum, right? As here also, we try to find the value of x, which will make fx minimum, right?
Right, yeah.
So this is how we solve it analytically, in fact. But in feed-forward neural network, it's impossible to solve it analytically. We need to solve it numerically. So we can use gradient descent for solving this problem, or error backpropagation to solve this problem. So we will initialize omega with some random values, and we will start updating those omega values, and step by step we can reach a minimum value. But I just want to refer to the fact that this simple function has global minimum and local minimum. So this function also might have also the same global minimum and local minimum. If you stuck in the local minimum, it will be a problem, right? So you can stuck in the local minimum, and your system will underfit your data because it does not have a chance to learn more, in fact, right? So when it's stuck in local minimum, it will not be able to learn anymore because the gradient becomes 0. And I will explain it in the next slide. So in the next slide here, I explain gradient descent, and we know gradient descent, I mean x will be x, I mean old x or x in u, sorry. So in fact, x will be equal x plus delta x, and the delta x here, it will be minus eta or minus zeta multiplied by delta f df by dx. So this is the equation which we will use in gradient descent, in fact. Minus because it's a gradient descent, not ascent. And this one, it's a step size or learning rate, which we need to use, in fact, for adjusting our, for updating x. So in each iteration, I need to calculate delta x, and I need to update the value of x. And we will start from some random value. And we hope that after some point, we will be able to reach this point, right? So I can give you an example. Okay, because this is the code which I did, but before doing this, I want to give you an example. I hope if you can see my, I want to share this whiteboard. How can we? So do you see my whiteboard? Do you see this whiteboard, please? Do you see this one? Can you see my whiteboard?
We still currently only see your screen.
Okay, you cannot see this. Okay, because I'm sharing it right now. You cannot see it. You cannot see him writing something here. You cannot see it.
No, just
Yeah.
Okay.
There.
Okay. So this is very simple function, f of x equal x squared. So I will plot this function here. It's convex, and I will solve this function, in fact, using a gradient descent. And as we mentioned before, that we need to get f dash of x. So f dash of x, which is the gradient, it will be 2 times x, right? So now I need to solve this problem using a gradient descent. So the equation will be like this one: x equal x plus delta x, and delta x will be minus learning rate multiplied by f dash x, correct? So it will be minus 2 eta multiplied by x, right? So this is a gradient descent. So now can you pick any point, please? Can you just pick any point by random? Maybe from -3 or -2. I can start from -2, for example. Imagine that I will start from x0 equal -2. So I pick this point. I have this point. And I need to start solving my problem. So first, for this problem, I need to find the delta x of 0. I need to find this value, f dash x0 equal, it's 2x. So 2 times 2, it will be -4, right? And imagine that the learning rate equal 0.5, right? 0.5. So in this case, delta x will be minus 0.5 multiplied by f dash of x, which is -4. So this one will be +2, correct? So delta x equal +2. I need to update my x value. So x equal old x plus delta x. So it will be, what is x dot? X dot, it's equal -2 plus the new delta x, which is +2. So this one will be 0. So now I will jump in one step. Unfortunately, it was not good choice to select 2 and 0.2, but anyway, now we will go directly to this point, right? Which is the minimum value. So now x equal 0. And when x equals 0, my function is minimum, in fact. So now I need to go to the next step, because I need to continue updating. So I will calculate f dash x, I will call it x1, for example. So f dash x1, it will be 2 times x, it will be 0. So the gradient becomes 0, right? And when it becomes 0, it means we will not be able to move away from this point. We will stuck here. And this is good solution because this is a global minimum of my function. So we did it in 2 steps, unfortunately, in 1 step or 2 steps. It would be better to select start from -5, for example. But is it clear how can we do it? We can do it one more time, but using more steps. So this is my function, x square, and f dash of x will be 2 times x, right? I will plot my function again, but this time I will start from another random value. Imagine that I started from -5, and learning rate will be 0.5, right? So in this case, I mean the equation which we will use for solving this problem using a gradient descent, it will be x equal x plus delta x, and delta x equal minus eta multiplied by df by dx, which is 2x. So this one will be -2 learning rate multiplied by x. So I selected x0 by random equal -5. So in this case, delta x0 will be -2 times 5. It will be 10 times 0.5. Sorry, x equal 5. So 5 minus 5 times. So it will be just what will be delta x? Maybe you can select. Sorry, we can select this one equal just 0.1 to make some steps. So eta equal 0.1. So in this case, delta x0 it will be -2 times 0.1 times x, which is -5. So this one will be it will be 1. x0 will be 1, correct? So the new x, I will call it x1, will be x0 plus delta x0. It will be, what is x0? It's -5 plus delta x0, it's +1, so it will be -4. So now we are moving, in fact. Now my next step will be -4. So now we are moving here at the point, you see? So I started here, now we are here. We will do it one more iteration, for example. So I will call it x2. So x2 will be x1 plus delta x1. So it will be x1, it's -4, plus delta x1. Delta x1, it will be -2 times learning rate 0.1 multiplied by -4, right? -4. So it will be, this one, it's a -8, it's a +8. So it will be -3.2. So now the next step will be, do you see? -3.2. So now we are here. And we will do this one step by step until we reach this point, right? At that point, the first derivative of the function will be 0, in fact. So we can say that delta x will be 0. Delta x all time will be 0. When delta x will be 0, see, you will stop here. So we will just go for some iterations until we reach this point. And then when we are reaching the global minimum, we will stay here forever, right? Now we finished. So this is how gradient descent work. And this is how I implemented, in fact, in the example. So if I can share, do you have any question for this part, for the mathematical part, for the gradient descent? So I will share my slides one more time. Okay. So this is how I implemented it in Python, in fact. So this is my function. I'm selecting a complex function for one reason. It's just because this function has local minimum and global minimum. So in fact, I'm selecting this function because of this. I'm selecting this function because this function has this one, it's a global minimum, and this one, it's a local minimum, right? And in fact, your solution will be based on the initial start, I mean the initialization of your algorithm. So this function, it's just f of x. I defined f of x here. And this one, it's df by dx, right? This one, it's df by dx, right? And I'm just selecting alpha, for example, or eta, for example. This is a learning rate. I selected very small value because I want to have more steps. and I just did some iterations. So x equal x minus eta multiplied by df, the gradient. Just ignore that part here. That part here, in fact, it's momentum term. This one here, it's momentum term. So in fact, how can you solve it? I'm just initializing. I'm selecting a point by random. So if you will start here, if I will start at +2, so I'm selecting here. In fact, I'm selecting here x0 equal +2. When x0 equal +2, I will start from this point, right? We will calculate the gradient. We multiply the gradient by negative because it's minus eta multiplied by the gradient. So we will move against the gradient until we reach this point. When we are here, we will stop here. Why we will stop here? Because the gradient here becomes 0, in fact. The gradient here becomes 0. So in fact, delta x here will be 0 at that point. So we will stuck here. So this is the problem. I mean, when you are using those numerical approach, there is no guarantee that you will reach the global minimum. We don't know. I mean, no one knows. You need to run your code several times to be sure that you are not in a local minimum. I need to jump. You cannot jump from here. In fact, it's hard. I mean, there are some approaches to do this, but maybe those approaches, they will work for your problem. Maybe they will not work. So anyway, when you start at x0 equal 2, you will reach this global minimum and you will stay here. Why we will stay here? We will stay here because delta x here at that point is equal 0. So there is no more updates. If you will keep running your program for more iterations, you will get nothing, in fact, because each time x equal x plus delta x, but delta x equals 0. So we will stay here. So in this one here, I'm selecting another random start point. If I will start here at x equal -6 from the other side, we will reach this point quickly, and we will stop here also because here delta x equals 0. But we are lucky here because this point it's the global minimum. We have here the momentum term, and this is a momentum, I mean, variable or factor. So this momentum term, in fact, it's a way to try to get rid of this one. You just try to have a memory and memorize something from the history because it's the current x minus the last x value. So we need to keep momentum and to keep a memory of last values, hoping that those last values are large enough to push you to get out from this trap. So this is the idea from the momentum term. But as I told you, it might help, it might not help. This alpha value also, which value will work with us, we don't know. Maybe 0.5 will work, maybe 0.7 will work. Maybe it will not work with you at all, right? So it's problem by problem and case by case. You have the code here. You can just go to the code here in GitHub and you can just run it and make some changes. So you can play with the eta value, with the alpha value, number of iterations. You can select a different function, for example. But this is how gradient descent works. I repeated this one, in fact, for more complex function because this function, it's 1D function. 1D means in this one, we have the x-axis, and in this y-axis, we have the function itself, which is f of x. So my function, it's function in x, only on x. If you want to play with 2D function, in this case, you can just get a function which is function of x1 and x2. In this case, we need to plot it in 3-dimensional space. In this axis, we will have x2, this axis will be x1, and in this axis, we will have the function itself, x1 and x2. So we can plot the function in 2-dimensional space. Once you plot the function, you will implement also the algorithm in the same approach, and you need to select a starting point. Maybe I'm selecting the starting point here, and after some iterations, you will go down to the global minimum of the function. So now we can minimize the function numerically, in fact. Right? And it's simple because I have two values. I have the function, it's function of x1 and x2. So we need to get the gradient, in fact. We need to get the gradient for each variable. We need to get delta f or df by dx1 and df by dx2. So this part here, this is df by dx1. And that part here, it's df by dx2. And we update x1 and we update x2. in a separate way, or you can just put them in a vector notation. In feed-forward neural network, we make it in vector notation, in fact, and we can update x1 and x2 in the same step. So x1 equal x1 minus eta multiplied by df by dx1, x2 equal x2 minus eta multiplied by df by dx2, right? So this one should be very straightforward. This function, it's 2D function, right? I will show you how feed-forward is more complex. If you have a feed-forward of, for example, one hidden layer of 3 units and one output layer of 2 units, and we have here input layer which has 3 inputs, for example, and just make all those connections. So how many weights? How many weights we have here? Can you calculate? So in this case, in fact, we will have number of weights. It will be 3 times 3 plus 3 bias. So this is the first hidden layer. The output layer, it will be 3 times 2, 3 times 2 plus 2. So now it will be 3 times 3, it's 9, plus 3, it's 12. 12 plus 6, it's so it's 20 weights. So this simple feed-forward neural network, it will be function of, the error function, it will be in 20-dimensional space if you want to plot it. It will be really something very complex. This function, it's 2D function, it's easy, we can visualize it. But in case, even for a very simple feed-forward neural network, it will be really very complex to display how the error function will look like. E equal half t minus y squared. So this is our loss function, which we try to minimize. This one will be very, very complex to visualize. Because in fact, this one, it's function of 20 weights and bias values. So it will be really very complex. So the momentum term, we adding here the momentum term. I added it last time. We have alpha multiplied by delta xi, in fact. So the convergence of the gradient descent may be very small if the curvature of the optimization is such that there are regions that are broadly scaled. Sometimes we have this bumpy surface. So gradient descent with momentum is a method that introduces an additional term to remember what happened in the previous iterations. This memory dampened gradient updates. So we can just add this momentum term. So just, I added here already. In this example, we have this momentum term here. So just adding alpha multiplied by delta x, right? All the delta x. So it's just a memory, and you can use. It's memory. So if it is a memory, we can decide how deep we need to remember. I can remember the last iterations, the last 2, 3, 4 iterations. I know that I have bumpy surface like this one, so maybe I need to remember more values from here. So when we remember more values from here, it will be important to try to get out from this trap or this global minimum. So the alpha, the coefficient, this momentum coefficient, it's number between 0 and 1. When it's 0, it means no momentum. When it's 1, it means we use full momentum. And this alpha value also, it's a hybrid parameter. You need to, you select it maybe by trial and error, or you can use an optimization algorithm, for example, search grid, to select a good value for alpha. So before starting in back propagation, do you have any questions for this gradient descent? Any questions? I described those gradient descent before, and we took some simple examples, but I tried to revisit it one more time before talking about error back propagation. So any question, please? Maybe you don't need to implement the gradient descent, but maybe no one knows. Maybe in the future, maybe you will do it. You will use it for something. It's the same also for error back propagation. The most important is to understand the concept behind it. But usually, you will build your model from Keras, for example, from PyTorch, for example, sklearn, for example. All those things are implemented. So you just need to know how to use it, right? but also it's important to understand the concept behind it and how those error backpropagation works. And what does it mean, global minimum and local minimum, and how can we get rid of, how can we try to escape from those local minimum? So it's just to understand what is going on behind the scene. So error backpropagation, it's a way to find a good set of parameters by performing this gradient descent. But we will do here gradient descent on a large scale. I mean, we did it for a function in 1D and function in two-dimensional space. But when we have a feed-forward neural network, it will be really more complex. And we need, it will be more complex even to visualize, right? So I suppose that I have this this feed-forward neural network, and it has one hidden layer. So this one, it's hidden layer. I will do it for this one, which is very simple. I have an input layer, and the input layer, it do nothing. It's just transfer inputs into the next layer, and I have here two inputs, and I have one hidden layer, and this hidden layer has two units, 2, 3, 4. We don't care, and we have here an output layer, and this output layer has two units. So we imagine that we have two classes. For example, you have bias. The input to the bias will be +1. So you can consider this +1 as an input, or you can just, if you want to update all weights in one line. So if you want to update all weights and the bias in one step, you need to include this one in the input vector. So the input, instead of being x1 and x2, it should be x1, x2, and +1. So I can just say, okay, this one will be x1, x2, +1. If you want to include the bias into the weights in the updating process. If you want to update it in a separate line, so in this case, I can just consider the input will be x1 and x2, and I will update the bias in a different line. I need to the output here will be h1 and h2. I mean the output from the hidden layer. We need to the weights here, it's omega1. So weight values here, it could be like this one, those weights. So it will be omega1 1, omega1 2, omega2 1, and omega2 2. So this is the weights. And for V, it's the same. V here, it will be the same. So V11, V12, V21, V22, correct? Like this one. If we will go forward, we need to go forward first to calculate Y1 and Y2. Y1 and Y2, it's predicted classes or labels. And once we have Y1 and Y2, we can calculate the error function. So as I told you before, the error function will be half multiplied by T minus Y squared. T, it's the target class or target label, and Y, it is a predicted one. And all time we try to minimize the difference between the target and the predicted. This is the whole task from learning. So the whole task from learning is to try to minimize the difference between the target and the output, right? So first we need to calculate Y, because I need to calculate the error signal. So we need to go forward to calculate Y, and after that we will calculate this error value, and we will go backward adjusting the weights. Going forward, it's very simple, because I just need, as we did before with a perceptron, we need to calculate the summation here. I mean, first we need to calculate the summation, and after that apply the activation function. How can we get the summation? I will call the summation net. So I will call it net equal omega x plus b. Simple, right? Omega, it's a matrix. X, it's a vector. B, it's a vector. So if I want to write it in more details, it will be like this one. Omega 1 1, omega 1 2, omega 2 1, omega 2 2, multiplied by x value, which is x1 and x2. So omega 1 1, omega 1 2. So this one should be transposed multiplied by x1 x2 plus b1 and b2. So it will be like this one, right? So net will be a vector of values. It will be like net 1 and the net 2. And after that, I need to apply the activation function here. So h will be 1 divided by 1 pi exponential minus net. Do the same, it will be v times h plus the b vector here for this output layer. So in this case, we will calculate the summation here. We will apply the activation function again, and we will calculate y1 and y2. So we go forward to calculate y1 and y2, and after that, calculate the error signal, and we need to go backward for adjusting the weights. once you have this error value, once you have this one, I need to adjust first the weights of this layer. So I first we need to adjust V1 and V2, V21, V22, right? So to adjust V, we need to calculate delta V. So I will just write it like this one, V equal V plus delta V. We know this from gradient descent. So what is delta V? Delta V minus eta multiplied by partial E by partial V. So simple, correct? So V equal V plus delta V equal minus eta multiplied by partial E by partial V. How can we get partial E by partial V? Right? It's easy. We need to use something called the chain rule. So partial E by partial V, it will be, because there is no direct connection between E and V, so we will take it step by step using this chain rule. So first I will get partial E by partial Y, and I will multiply it by partial Y. Y, it's the activation function. So this is Y, in fact, 1 divided by 1 plus exponential minus net. So in fact, Y is function of net. So it will be partial Y by partial net. And what is net? Net, it's only X plus B. So from this one, I can get partial E by partial V, or Vx plus B, right? So it will be partial net, partial V. Now we are done. So we need to get partial E by partial V, because this is a gradient, what we have learned from gradient descent. We need to get partial E by partial V. We will use something called the chain rule. This one, we call it chain rule. This chain rule, it will help us to get partial E by partial V. Partial E by partial V, it will be partial E by partial Y first, multiplied by partial Y by partial net, multiplied by partial net by partial V, right? So this is how we will do it. So if we need to get more details, we will start by, so this is, I just mentioned this, right? Correct? So delta V, it will be minus eta multiplied by partial E by partial V. We will use a chain rule. So this one will be partial E by partial Y multiplied by partial Y by partial net, multiplied by partial net by partial V. We will call this one delta Y, right? Delta YK or just delta Y. We just give it any name. When we calculate it, we call it delta, right? So first, we need to get, we have E, we need to get partial E by partial Y. Partial E by partial Y, it will be Y minus T. Why? Because partial E by partial Y, it will be 2 times half, which it will be 1, multiplied by T minus Y, multiplied by the first derivative of T, which is 0, multiplied by the first derivative of minus YK, which will be minus 1. So it will be negative, multiplied by TK minus YK. So you can just multiply negative, put negative inside, so it will be Y minus T. So partial E by partial Y, it will be Y minus T. Now we need to get the next part. The next part, it's partial Y by partial net. This is Y and this is net, or X, or Y equal 1 divided by 1 plus exponential minus net. So partial Y by partial net, it will be, in fact, this is how we can get it. It will be Y times 1 minus Y. So it will be Y times 1 minus Y. Now we got the second term. The third term, partial net by partial V, extremely simple, because net equal VH plus B. So it will be H, I mean net in general. It's V times H for this layer plus bias, for example. So partial net by partial V, it will be H. You can just give it any notations, any names, right? So now we have 3 equations. So we need to construct delta Y. Delta Y, it will be partial E by partial net. So it will be this one, Y times T, Y minus T multiplied by Y times 1 minus Y. So now we have delta Y. If you have delta Y, we can write this equation now. Now it's much easy. Delta V equal minus eta multiplied by this delta value multiplied by H. Now we have the equation for adjusting the weights of the output layer, right? If you want to do it for, I mean, in this example, in fact, I included the bias with the weight. But if you want something for the weights, I can just call it delta BJK. It will be minus eta multiplied by delta YK, right? if you want to adjust the bias in a separate line, because here we are multiplying by h. It will be the output from this one and this one. If you are updating the weights, if you want to update the bias, you need to multiply by +1. So it will be like this one. And in similar way, you will do it also for delta Ig. You will do it for this layer. So we go backward layer by layer and adjust weights. I told you before something about vanishing gradient. What is vanishing gradient? Vanishing gradient is this delta value. I mean, this delta value, do you see? This delta value, it's y minus t, it's error value multiplied by the activation function multiplied by 1 minus the activation function. Do you see? This is the delta value. This is the problem, in fact, in vanishing gradient. If you want to adjust the weights, it's minus learning rate multiplied by this value, multiplied by input. Input, we don't care about the input because the input, it's an input signal. We get this from dataset. So the problem here in delta yk, this value, and this value, in fact, it's error signal multiplied by y, multiplied by 1 minus y. Imagine we are using a Gaussian, right? So Gaussian value, anyway, it would be a number between 0 and 1. So 0 and 1 multiplied by 1 minus this one, right? So it's a small values multiplied by small values all time. So this delta value will get smaller and smaller each time. And even when you do it for the hidden layer, if we need to calculate this new delta h value here, it will be also multiplication of those weights. I mean, delta value here, it will be multiplication of those delta values with those weight values, right? So this value will get smaller and smaller and smaller. So if your neural network is too deep, I mean, those values will be okay for adjusting those weights here. It will be fine here. But if you want to go deeply and adjust the weights here, it will be less effective, in fact. And if you have two hidden layers, it will be less and less effective. So when you go deeply, it will be a problem because at some point, this delta value will become 0. And in this case, it will not help you to adjust your weights. So do you have any question for this error backpropagation algorithm? I mean, the next part, it's just implementing it. I implemented it by myself, in fact. And also I'm sharing the code with you. This one, it's error backpropagation. And I applied it to Iris dataset. So I just implemented it as stochastic gradient descent. So we need to what is stochastic gradient descent? What is batch gradient descent? What is mini batch gradient descent? I mean, it's a proposed question for the oral exam. I mean, in the oral exam, I can just ask you what is the difference between SGD and the batch gradient descent and mini batch gradient descent, right? So those kind of questions you need to understand it. So I just implemented it as stochastic gradient descent. And in stochastic gradient descent, in each epoch, we go through the whole data set and we go forward and go backward to adjust the weights for each example, right? We adjust the weights of my neural network for each example. So for example, if I have 100 points, if I have 100 examples, right? So in each epoch, I will update the weights 100 times. But if it is batch gradient descent, so you will update the weights only one time in each gradient, in each epoch, right? We use a minimum average gradient and update only one time in each epoch, right? If it is mini batch, it's according to the batch size. So if I will select the batch size equal 20, so in this case, we will update 5 times in each epoch. So in the last years, I had this kind of questions. I just ask the students, you have a data set of this size, and we will train the model for, first I have 2 hidden layers, and this is the input, this is the output. Please calculate how many parameters we have in the model. So we'll just calculate the parameters as I did today in one of the examples. You will say, okay, this example has maybe 5,000 parameters, for example, we need to adjust. And if it will be stochastic gradient descent, so we will have those number of updates, because if it is a stochastic gradient descent, we will do those calculations for each parameter. We do it in matrix notations, but how many calculations, how many multiplications and stuff like this, you can count number of weights by number of examples, by number of epochs, for example, if it is a stochastic gradient descent. So you can discover that it will be a huge number of calculations, lots of calculations. But if it is a batch gradient, no, we will do it one time in each epoch. If it is many batch gradient, so we will do it a number of mini batches. So it's the data size divided by the batch size to get number of updates in each epoch. So we can do lots of questions and lots of stuff from this one. So those definitions are very important to know what is SCGD and what is the difference between SCGD and the BGD and the mini batch gradient and so on. So in this example, I implemented it SCGD. So I just I have number of epochs. I defined a number of epochs, and I do it for the whole data set, right? So we have this for loop because I need to update for each data set, and I go forward. This block, in fact, just to calculate the output. This is the forward pass, right? So this is the forward pass. We go forward, and after that we go backward for adjusting the weights. I mean, this one it's backward. So we go forward to calculate the output, and we go backward to adjust the weights. Adjusting the weights is a bias of each layer. I did that for one hidden layer. If you want to make it more complex, you can just decide to go for 2 hidden layers, for example, and make it more complex. So in that part here, I need to calculate, I need to go forward. When you go forward, I need to calculate first net. Net, it will be X. I mean, the equation here, it will be XH or X, sorry, X, it's omega X, sorry, it's omega X plus B, right? And after that, I will apply the, I mean, this Gaussian function, which is 1 plus 1 divided by 1 exponential minus net. So this is net. And I will do it for each layer, right? I will do it for each layer. But in the first hidden layer here, we use X, the input. But in the second layer here, in the other layers, we use the output from the previous layer. So the output here, it's output, I call it output H. So I will use this output H, multiply it by those omega plus B, and I will apply the activation function. So if you want to implement error backpropagation, it's very important to select an activation function which can be differentiated, right? So you need to select an activation function which is easy to differentiate. Of course, if you are using, I mean, if you are using Keras, for example, or sklearn, you can just select ReLU, Gaussian, hyperbolic tangent. You can just select because it's already made. So we're just using it as a user or as a black box, for example. So you just need to select the kind of activity. And I mentioned before that the selection of the activation function, it should be based on the data, right? What kind of data you are working with. Because the activation function has huge impact on the amount of information which will be transferred to your model from your data. So for example, if you will use Gaussian has this squashing impact, right? So we will lose lots of information if we didn't normalize our data set. If you will normalize, it's fine because all data points will be numbers between 0 and 1. In deep learning, we don't normalize, we don't touch the data, we just work with raw data. So in deep learning, usually people use different activation functions similar to ReLU, rectified linear unit. So we will go forward for calculating the output, and after that, I will calculate delta O. Similar to the equation which we did, it will be output minus T, Y minus T multiplied by output multiplied by 1 minus output. So it's exactly the same like the equation which we got. We will calculate delta H also. Delta H, it will be omega multiplied by delta O. So delta H will be omega multiplied by delta O. And after that, multiply this delta H by output times 1 minus output. So this is dy by d net, right? This is dy by d net. And after that, we will adjust the weights. So omega equal omega minus eta multiplied by x multiplied by this delta H multiplied by the input. And for the bias, it will be minus eta multiplied only by delta H because the input for the bias is +1, right? We will do the same for, the other weights and the bias. It will be this eta multiplied by delta H multiplied by the input of this layer, output of the hidden layer. And also the bias, it will be just the same. And after that, I will do some evaluation after each epoch. So we need to keep the training error and the validation error and the testing error, right? So I will just, I mean, each time after each epoch, I need to check the accuracy. When should we stop? Because maybe we have some overfitting or underfitting problem, or especially overfitting problem. So I need to test my model. So after each epoch, I send X training and X validations and X test and get the predictions. And I need to calculate the prediction error for the training set, for the validation set, for the test set, for each epoch. And after that, plotting it. So when I implemented this problem, and when I applied this problem, I call it feed-forward, in fact. So I call it here feed-forward neural network. And you need to specify learning rate, eta. You need to specify the number of epochs. I selected 100, for example. You need to shuffle, because remember, our dataset is not shuffled. I mean, if you are working with Iris dataset, the first 50 examples are class 1, the second 50 are class 2, the last 50 are class 3. So we need to shuffle. And I just used the one hidden layer. So if it is only one hidden layer, we need to specify how many units, how many neurons in this hidden layer. Validation set, we are dividing the data into training and testing. And also we need to get a validation set. The validation set, it's apart from the training set. And we use it to validate our model or to fine tune the model hyperparameters, right? It's a data set which can be used as a testing set for the training set. Use it after each epoch to check the accuracy, for example, of my model. So I mean, this is what I have implemented here. We have X train, we have X validation, we have X test. And after each epoch, I make predictions. Of course, at the beginning, maybe the accuracy will be very bad, but after a few epochs, the accuracy should be improved. So I need to see this. So I did that using X train and X validation and X test. X test, it's hold out validation. So we just keep it out, because after training the model, I need to test the accuracy of my model. For the training and the validations, it's very important, because from those values, we can discover if the model has an overfitting problem or not. So from my training dataset, I need to take part from it, and I will call it validation training validation set. And this validation set will be used for testing the model performance after each epoch. So I did that for Iris dataset. In the Iris dataset, I proposed a very simple feed-forward neural network. So the neural network will have 4 inputs, because we have 4 features in Iris dataset. And I mean, today I just used the one-hot encoding. So this one will be class 0, this one will be class 1, this one will be class 2. I use the one-hot encoding. So if you want to use any kind of encoding, it's up to you. In binary encoding, it will be much simpler, because it will be 2 bits, right? It will be just maybe 0, 0, 0, 1, 1, 0, like this one. If you want to use 2, of course, it will be something like this one. So I used this simple feed-forward neural network. How many parameters here? Can you count how many parameters in this model? How many weights? So in the example in front of us, this one, can you mention, please, how many weights we have?
36, if I'm not mistaken.
20?
36.
36. Okay, we will calculate it. So it will be 4 times 4, correct? 4 times 4 plus 4 for the hidden layer, plus this one, it will be 4 times 3 plus 3. So it will be 4 times 4, it's 16, plus 4, it's 20, plus 3 times 4, it's 12, plus, so it's 15. So it's 35, right? Is it correct? So it's 35 weights. 35 weights.
Yep.
So in the graph here, we can see the training. I'm plotting here the accuracy, in fact. So I'm plotting the accuracy. So we have the training accuracy, validation, and testing. And from very, very important to look into the training and validation, in fact. So the blue one and the green one, they are very important, right? Because what can happen here? What should we expect? If for example, the training was like this one, so the training was improving, and after that it will improve a lot, just improving. But at the beginning we have the validation, it was very good, and after that it goes down. So if this one it's the validation and this one it's the training, it will be overfitting, right? So the training, we should expect that the training will improve all time, right? So, but if the validation is improving and suddenly it starts to decrease, it means the model is just memorizing my dataset and it's overfitting my dataset. So we need to keep an eye, in fact, on the training and validation. And we have a technique called early stopping. So when we have this case, in fact, we can stop here because model overfits. We need to go back, in fact. So we can stop training after 4 epochs or 5 epochs. But we cannot continue training, because if we will continue training, the model will overfit my dataset.
So would you want to stop the model, stop the training at the intersection between the training and the validation, or would you want to stop it at the peak
Before.
of the validation?
No, before, because when it's intersection, in fact, it means that the accuracy is going down, right? So we need to stop maybe one epoch before or 2 epochs before.
So you wouldn't want to, for example, in the thing you've drawn there, you wouldn't want to stop at the peak of the validation. Wouldn't that presumably be the
yes
optimal value?
For example, yeah. So because we have the peak here and it started to go down now, right? So if you can stop at the peak or close to it, it will be fine, right? But because here at the cross point here, it's a situation is very bad because it's going down anyway now, right? So when you feel that the validation accuracy started to go down, you need to stop some epochs before, maybe 2 epochs before or something. And they implement it in this way, in fact, in Python. So you can go back, maybe they store the weight values, maybe in the last 2 epoch or 3, 4 epoch, for example. And when you feel that you have, you have overfitting, they will just go back. They will stop, and they will go back maybe 2 or 3, because we have already stored those weight values. So early stopping, it's a very nice technique, and this early stopping, it will keep watching the value of the training and the validations, and then when it feels that the model will start overfitting your dataset, it will stop and it will go back. In fact, maybe 1 epoch, 2 epochs. I don't know how they implemented it, in fact, but it should go back maybe 2 epoch or something. You need to check, the documentations of early stopping, how it works in each package. So we need to stop training, because if we will continue training, the model will just memorize my dataset and it will not able to generalize, in fact. The performance, as you can see here, the performance is very good. I have some examples, in fact, maybe for next week, for lecture number 8 or something. So the model, if you keep training, the model at some point, it will just memorize the training dataset, and it will not be able to generalize for never seen before data points. So we need to stop at some point and just go back maybe to epoch or something for previous weight values. So we want to ignore maybe the last 2, 3 updates, for example. Yes. So, and the accuracy here, it's 19.27%. Maybe it's not good enough. We need to reach maybe 98%. So you can just play with this code. You can try to add more units here, right, to make it more. Maybe you need to increase the model complexity because accuracy is not good enough. Maybe there is a chance to improve it, for example. Maybe you need to add another hidden layer. If you want to add another hidden layer, you need to go back to this code and just add 1 more hidden layer. So it will be 2 lines here, right? And also maybe because 2 lines here also, we need to calculate another delta and another 2 lines for updating the weights and the bias. So one way, if you want to play with this one, you can just go to this code and try to make it more complex, right? Make it more general. Make it like Python functions, because I call it feed forward now. You can just make it more nice and more robust, for example, and you can ask the user to decide how many hidden layers and how many units in each hidden layer. You can add also here momentum term. For example, I didn't add momentum term. Maybe we need to add momentum term, right? You can implement cross validation. For example, I used here SCGD. You can have those options, all those options. So if you want to make it more complex, you can make it in fact more complex. We did it for Gaussian activation function. You can do it for different functions, and the user can select which function he want to use. So if you want to make it more complex, you can just make it more complex. Yes, I guess we finished this part, and I mean, after the break we will go to something about unsupervised learning, because we have been talking a lot about supervised learning. So we need to check some unsupervised learning techniques, and it will be after the break. So do you have any questions or any part or any comment on that part? You have the code for MNIST dataset, and for this Olfetti face recognition dataset, you can just replace the dataset with this new dataset and try to play with the code, try to develop it, try to achieve very good accuracy, try to apply BCA, for example, right? Or autoencoder for dimensionality reduction. I will talk about autoencoder maybe next week. No, maybe today, if we have time today, maybe we can talk about autoencoder today, because autoencoder, it's an unsupervised learning, in fact. I mean, in machine learning, we have supervised learning and unsupervised learning. Autoencoders, it's similar to BCA also. BCA, it's unsupervised algorithm. Autoencoder also, it's unsupervised algorithm. And we use autoencoder for denoising or for dimensionality reduction. So do you have any question for this part? So you can just, I mean, bring your coffee, and we can take 10 minutes break, for example, or 15 minutes break. We can start again at 12. Is it fine?
Yeah, that sounds fine.
Okay, thank you very much. So we will meet again at 12. And please prepare your questions. If you have any questions, just prepare it, and let us discuss it after the break. Thank you very much.